Hello, can you guys hear me? Hello, can you guys hear me? All right, so let's give it one more minute while we're receiving more attendance. Okay. Because today is a new lecture of our new session. We always have some new student joining us. From time to time, we might have some technical issues. So let's give it one more minute while we're receiving more attendance. Okay. All right, so let's get started. So welcome to our 2021 AMC10 AIME Core Preparation Bootcamp. So before we get started, because always we have some new student joining us for the new sessions, I'd like to spend roughly 5 minutes talking about our lecture. So try to give you guys some short and brief introduction about our organization, how it works, where we come from, and where we stand. All right, should be fairly quick. Okay, so this is our interaction. So the first one, I want to talk something about the strategy of our lecture. As you probably know, this is actually a boot camp for the AMC10 and the AIME exam. So for sure, we're going to consolidate all the knowledge into 10 lectures. There's so many concepts for the entire AMC. It is very challenging, if not impossible, for us to cover all the concepts. So therefore, we're going to pick up the most important, the most high frequently tested concepts that in the AMC and also in the AIME. And a lot of students keep asking me how are we going to do the problems. So to be honest, there are so many problems, right? It is impossible for you to cover them all. Well, on the contrary, the most important thing is we got to learn the technologies and the strategies to solve the problem. Pretty much the fish and fishing, right? The most important thing is for each problem, I'm going to tell you what is the basic thinking process. There are millions of problems. You can never cover them all. But as long as you see some problem, as long as you see some keywords from the problem, it should really trigger some of your nerves, give you kind of like a conditional react. So as long as you see this word, you're going to take all those actions. As long as you see such a condition, you're going to do such a problem, so on and so forth. So generally speaking, this is exactly what we're going to cover for our entire lecture. The concepts plus the strategies and the keywords in order to solve the problem. All right. The second one is the interaction. You know, these days, due to the COVID situation, I think you guys won't be so unfamiliar with the entire, online lectures, so on and so forth. And I think there's not so much differences between the online lecture and the face-to-face lecture, provided we have a good interaction. So think about it, even though you have the teacher standing right in front of you, but you don't ask for questions. So it's exactly the same thing. So interaction is always the important, or we can say the key point for our entire lecture. There are two ways for you guys to participate into my lecture. The first one, which is highly preferred, is you can actually just talk. When you enter the classroom by default, you'll be put into mute, but you can always unmute yourself. So for the entire lecture, as long as you have any questions, just try to unmute yourself and interrupt me anytime you like and ask me the questions. So whenever you ask the question, some other students, they can also see your question, hear your question. They might also be providing some solutions, so on and so forth. So this kind of interaction is actually very important for my entire lecture. Or the other option, if you feel a little bit shy, you don't want to have the direct talking, no worries, you can actually chat with me. I hope you guys should be familiar with the Zoom application, but if you're not, if you go to your control console, there mute, stop video, so on and so forth. On the very right end, there's a 3 dots, right? Click that 3 dots and you'll be able to see a chat in the pop-down menu. The first one, we will click the chat. It will bring you to the chat board. The chat board is actually very important for our entire lecture. I'll be monitoring the group chat board all the time while in my lecture. If you have any questions, you can feel free to post it into the group chat. You have 2 ways to put your answer or your problems. First one is you can choose to everyone. I think by default, like the chat board is going to send your message to everyone, that everyone can see it and give you the inputs. Well, if you want to talk to me individually, you don't want to be your message to be seen by the other students, no worries. You can choose my name from the drop-down menu. This is going to be a private message between you and me. So I will see your message and I will give the answer directly for the entire lecture. So there are 2 ways, but generally speaking, I think directly unmute yourself and ask me the question. This is going to be something very important. Okay? The last one is the homework. So mathematics is actually a very practical, I'll say like a practical science. If you only listen to my lecture, but you don't really get your hands dirty, this is going to be very difficult for you to learn all the technologies. So therefore, after each lecture, I'm going to give you some problems as a homework. You have 1 week to finish up the homework. And as long as you're done, you'll be able to submit your homework into the Google Classroom. I will mark your grade, I will give you the comments, and most importantly, from the next lecture, at the very beginning, I will be asking students to basically give us some solution, present your answer to the other students. So don't be shy and no worries, as long as I call you means you did a good job. So I won't make you like a fool in front of the other students. When I call you means you did it correct. So you should be more than confident. And like the reason behind that is these days, if you only know the knowledge, this is not enough. The presentation skill is actually way more important compared with just knowing the knowledge. I don't know if you guys want to go to some big techs in the future, let's say Google, Amazon, Facebook, so on and so forth. So when they're doing the coding interview, the most important thing is not really give a computer, you scrambled in the shabby room, do the coding. On the contrary, they will let you to put your code onto the whiteboard. So that being said, as long as you're coding, you need to think aloud, walk through the employer for the entire process. So this kind of presentation capabilities, especially important, I think these days. So I really take any steps to make sure everyone can have more opportunities to train these skills. All right, I think this is quite a short and brief introduction about our lecture. All right, so before we jump to today's lecture, this is actually the syllabus for our entire 10 lectures. Like I mentioned, there's so many concepts for the entire AMC and AIME. It is very challenging for us to cover them all, but I have already picked up the most important things and break them into 10 different lectures. In the first 3 lectures, we're going to be focusing on the geometry part. The geometry is actually a very important part for the AMC. So we put 3 lectures talking about the 2D geometry, the 3D geometry, and coordinate geometry. And then another 3 lectures talking about the algebra. Again, algebra actually has so many sub areas from like the sequence, inequalities, so on and so forth, polynomial. There's so many concepts. We like to consolidate them into 3 lectures and pick up the most important, the highly tested problem for you guys to review. And then we're going to spend 2 lectures talking about the counting and probabilities, and the last 2 lectures talking about the number theories, which is the most challenging part for most of the students. Because in our day class, I don't think you're going to have any chance to learn the number theories. Everything that tested by the AMC or AIME exam needs to be learned individually outside our day lectures. So this is like a short and brief organization for our 10 lectures. So make sure we can cover the 4 very important chapters for the AMC, aka geometry, algebra, counting and probabilities, and also the number theory. All right, so I think this is a short and brief introduction about our organization and how our lecture works. If all good, let's jump to our first lecture, 2D geometry. Okay, this is going to be our lecture number 1, 2D geometry. All right. So for each lecture, it's going to be organized in such a way. Before we jump to the problems, I'd like to spend some time, give you guys some organization, organize and summarize the most important concepts that you need to know for the AMC10 and also AIME exams. So let's go to our first section, concepts. There are some knowledge that you need to know in order to go for the AMC10 and AIME. So this is the first one. Triangle, inequality. As long as you have a triangle, A, B, C, then automatically you're actually going to have two different inequality relationship. The first one is going to be A plus B greater than C. The other one is A minus B lesser than C, right? These are the basic concepts that you will know for the entire triangles. And also, on top of this, there are also a inequality hidden for all the triangles, which is the cosine law, right? Let's say if it's theta, so cosine theta will be equals to a squared plus b squared minus c squared 2ab, right? This is the cosine law. And this guy, if I take an absolute value, will be lesser than 1, right? So these are actually two very important inequalities for all the triangles, not necessarily a specific type of triangle. It's actually working for everyone. Sometimes the AMC problem will ask you an inequality relationship between any triangles. Then probably you're going to start your work thinking about these two directions. All right, this is number 1. Number 2, also very familiar, is the Pythagorean Theorem. Pythagorean theorem is actually something so familiar to you guys. I think you guys learned that from your elementary school. As long as you have a right triangle, a squared plus b squared, you're going to have a equals to c squared, a right triangle, right? And also, for one direction it works, for the other direction it also works. It means the Pythagorean theorem is okay for positive and the inverse theorem. All right? Trust me, in AMC, they won't directly test you the Pythagorean theorem, which is so direct, so conspicuous. But most of the time, AMC will test you to understand the Pythagorean triples. Pythagorean triples. What is that? It means that as long as I give you 3 numbers, they're forming a Pythagorean triangle, A, B, C, a squared plus b squared plus c squared, you should be able to recognize it right away as saying, hey, this is actually a right triangle. Okay, so how many Pythagorean triples you need to know? These are the most important things. 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17, 20, 21, 29. Okay, trust me, these are the most important Pythagorean triples. So in the problem, especially in AMC, we have a type of problem we call the rotation and the reflection. So this type of problem means that the problem is going to give you a shape, maybe here, and then you need to rotate the shape, maybe from here to the other place. Just want to give you guys an example, okay? After this rotation or reflection, you will be able to construct another pairs of triangles or quadrilaterals, so on and so forth. Most of the time, the question will give you a bunch of numbers talking about their segment, and you will luckily to realize after you do the rotation, you will be able to construct a right triangle. This is pretty much 90% the situation. Okay, from the right triangle, you'll be able to do all the works. But where you get the right triangles, you need to remember all those Pythagorean triples, because the question won't tell you, okay, this is a this is a right triangle. You need to recognize it by yourself. Okay, And not only for the basic form of this 3, 4, 5, 5, 12, 13, sometimes what about I times 2, right? 6, 8, 10. This is also a Pythagorean triple. What about I times under root 3? So try to remember the seed of the Pythagorean triple and do some elaborations on the fly. This is also very important for the AMC. All right, so let's continue. Number 3 is the famous Heron's formula. Heron's formula says as long as you have a triangle A, B, C, then you will be able to determine the area of the triangle simply using 3 sizes, right? You can define P equals to A plus B plus C divided by 2. So the area of the triangle can be written as under root P, P minus A, P minus B, P minus C, right? I think this is quite understandable for the Heron's formula. Well, here I want to give you guys a very important side note. Most of the time, AMC will give you such a scenario. I'll say 99% you will see such a scenario. The question give you A, B, C, 3 sized, and for some reason, the question asks you to determine the height on one of the side. Okay? So actually, there are 2 ways to do this problem. The first one is, say, determine the height, right? The first way I think which is the most conspicuous way is you can try to use the Heron's formula to determine the area, the entire area, right? And then the area will be also equals to 1 over 2 h times b. Okay, I think this is quite easy peasy stuff. Well, this is actually only one solution to do the problem. The second solution is you can use what we call a double Pythagorean theorem. What is a double Pythagorean theorem? You can try to think about this problem this way. In order to determine the value for h, I can actually let this guy equals to x. So this guy is going to be b minus x, right? So I will be using the Pythagorean theorem twice on the left-hand side of this triangle, and on the right-hand side of this triangle, I'll be able to have a squared minus x squared under root equals to c squared minus b minus x squared under root, right? You're using the Pythagorean theorem twice on the left and the right. They both give you the height, right? And after you have the value for x, you'll be able to determine the value for h, which is a squared minus x squared. Okay, it looks like the second way is more complicated compared with the first way, right? Because you have to do a lot of under root, so on and so forth. But actually, it is not the case. It really depends on what are the numbers given by the problem. If I give you a lot of easy numbers for ABC, 4, 6, 4, 3, 5, for instance, like this, okay? In that case, of course, you can use the Heron's formula. It's very straightforward. However, if the question gives you a lot of weird numbers, let's say I give you a number like under root 71, under root 29, under root like whatever numbers 1, something like this. In that case, if you use the Heron's formula, think about it. What are you going to have? Your P is going to be something like under this under root plus under root divided by 2, right? And then you want to plug in the P into such an under root. You're going to have an under root and then so many under root times together, right? This is going to be a disaster. You won't be able to solve it out so fair, so straightforward, right? So that being said, as long as you see some weird number, nasty numbers for the size, your first option is always using the double Pythagorean theorem. Because whenever you see this, everyone is going to help you to eliminate the under roots. Is that right? According to my experience, 80% of the AMC problem will ask you to use the double Pythagorean theorem. Only 20% you can directly use the Heron's formula. So always get ready. There are 2 ways. Okay? If all good, let's continue. Number 4 is the famous angle bisector theorem. Angle bisector theorem goes like here. You have a triangle ABC. You have an angle bisector, which is D, right? These two guys are the same. Then automatically you should have AB over AC equals to BD over DC, right? This is very important. Trust me, for all the AMC exams, regardless 10 or 12, as long as the question gives you angle bisector, then 100% they will use the angle bisector theorem. I never see any exceptions, so try to remember angle bisector theorem is the #1 important things. All right, we have talked about it so many times in our regular lecture, but this is our boot camp. We just give you guys something fairly quick, okay? And then number 5 is power of a point. Power of a point is not only one theorem, it's actually a series of theorems, right? It actually can be broken down into 3 parts. The first one we call is the chord theorem. Means what? If you have a circle, you have 2 chords intersecting in a circle, then you're going to have A, B, C, D. Let's say this is O. You're going to have AO times OC equals BO times DO, right? The 2 intersection chords will be basically you do multiple for one equals to multiple for the other. This is the chord theorem. The second one is the tangent theorem, right? Tangent theorem. Tangent theorem goes like this. When you have a point, you want to make a tangent, A, B, C, D, then automatically AB squared equals to AC times AD, right? This is the tangent theorem. AB squared equals to AC times AD. And the last one is the secant theorem. Secant theorem means you have 2 seconds, A, B, C, D, E, right? Both of them are cutting our circle. You're going to have AB times AC equals to AD times AE, right? Okay, this is like the basic form for our power of a point. And I like to give you 2 side notes talking about this. Side note number 1. Actually, if you do a comparison between the tangent theorem and also the secant theorem, you're going to find out the tangent theorem is only an exception for the secant theorem, right? So as long as you're moving this line a little bit go out, a little bit go out, all the way it comes to here, that part A is still here, and B and C will be superpositioning, right? If you're moving out, out, out all the way, the secant degrades into a tangent. So B and C will be superpositioned together. In that case, you see, AB times AC will become AB times AB, right? Because B and C will be superpositioning. So this is going to give you what? AB squared, right? So AB squared equals to AD times AE. This is exactly the same thing as our tangent. So tangent theorem is only an exception for the secant theorem. Okay? Our side note number 2. As long as you see tangent, basically there are 3 things you need to do. See tangent. Basically, you need to do 3 things. And as long as you do the 3 things, all the problem will be solved. The first one is do a connection between the tangent point and the center. Do a connection between the tangent point and the center of the circle. Then automatically you should have a perpendicular, right? Because your radius is going to be perpendicular for your tangent line. Second, whenever you see 2 circles, they're tangenting to each other, you do a connection between two centers. Let's say they are externally doing this. So you make a connection and check it out. When you do the connection between these two centers, so this line is going to be perpendicular for this tangent, right? Same thing applies if you do it internally. This is exactly the same thing, right? This is going to be perpendicular to the extension of two circles. And the last one is tangent secant theorem, right? So trust me, if you do analysis for all the AMC problems, you're going to find out these three actions, this is three actions which is going to help you to fulfill all the problems that are required by the AMC, and you should be good to go. Okay, this is I think this is our number 5. Number 6 important thing you to know is the Ptolemy, right? Ptolemy theorem says as long as you have a cyclic quadrilateral, A, B, C, D, you want to make a connection, you can have AB times DC plus AD times BC equals to AC times BD, right? So that being said, if you have a cyclic quadrilateral and you're going to have the sum of the product of the opposite side equals to the product of two diagonals, right? And this is the cyclic. You're going to have this. And this theorem is also valid for the other direction. It means if you have any kind of quadrilateral, as long as you have the sum of the product of the opposite two sides equals to two diagonals, then you can say this quadrilateral should be a cyclic quadrilateral. Okay, I think this is something that we need to know. Okay, moving forward, number 7 is the famous Stewart. The famous Stewart theorem. Stewart theorem is actually a very generic theorem for all those triangles, and it goes something like this. If you have a triangle ABC, and you have a dynamic point D on the BC side, it's a dynamic triangle, any kind of triangle with a dynamic point, then let's say they give a name C, this is maybe B, this is D, this is M, this is N, right? You're looking at 5 different segments, and there is a relationship between these 5 different segments, which is M times A times N plus D plus A plus D equals to B plus M plus B plus C times N times C. So this is the relationship for such a triangle. As long as you know 4 segments, you'll be able to determine the last segment. So there's a relationship between all the segments. So how to remember this? This is a little bit nasty, right? It's kind of difficult for us to remember. And there's a trick how to remember this. You can say a man and his dad put the bomb in the sink. This is a shortcut way for you to remember. A man and his dad put a bomb in the sink. You can always try to remember. You can always try to remember. Say that a man and his dad put a bomb in the sink. But don't say that when you cross the border, right? So this is actually a way how you can remember this Stewart theorem. And the Stewart theorem actually per se is a little bit nasty. It's a long form. If you really do not need to remember or do not want to remember the Stewart theorem, at least you need to remember 3 variations of the Stewart theorem. Or we can say 3 specific forms of the Stewart theorem. Okay, this is pretty much like extension 7.1. The first one is the famous angle bisector length formula. It means at this moment, AD is no longer a random guy. AD is actually the angle bisector, right? In that case, our original form will be degraded into AD square equals to AB times AC minus BD times DC. Because AD is already a angle bisector, we can use the angle bisector theorem help us to simplify some of the terms. This is the number one thing that you need to know. Number two thing you need to know is the famous median length formula. Means at this moment, AD is actually degraded into a median. In that case, you're going to have 2AB squared plus 2AC squared equals to BC squared plus 4AD squared. Okay, you can still determine the value for AD, right? AD. This is the second specific form that you need to remember. The last one you need to remember is whenever this triangle becomes what? An isosceles triangle. So this triangle ABC, they have AB equals to AC. This is an isosceles triangle. Okay, but D is still a dynamic point. So something goes like this. This is A, B, C. D is here, right? D is a dynamic point, but AB equals to AC. So that being said, you're going to have AD squared equals to AB squared minus BD DC. All right? So these are actually all between, all like for under the Stewart theorem. If you can remember the Stewart, you don't have to remember them one by one. But if you do not want to remember Stewart, at least these three specific variations, they are very important. If you know this is going to help you accelerate your calculation process significantly. All right. This is actually our number 7. So let's continue to number 8. Number 8 is the famous sine law and the cosine law. Okay, this is also very important. You need to remember from time to time, they will test it. The sine law says A over sine A equals to B over sine B, C over sine C, that equals to 2R, right? This 2R is what? My triangle A, B, C, right? This is A, this is B, this is C. This 2R is actually the radius of the circumcircle, right? R is the radius of the circumcircle. I put R here. This is the famous sine law. The other one is the cosine law. Cosine law means as long as you have a triangle ABC, then cosine A will be equals to B squared plus C squared minus A squared to BC. Cosine B will be equals to C squared A squared minus B squared to CA. Cosine C will be A squared plus B squared minus C squared to AP. All right? Cosine law is actually a very important tool for AMC12 and AIME. AMC10, they don't ask you very often, I have to say, not as often as AMC12, but our lecture is actually combined lecture. We're going to go to the AIME, right? So if you get selected from AMC10, whenever you go to the AIME, they will give you the same AIME. The AIME exam is the same thing for 12 students and 10 students. So you still have to remember this if you want to do a good job for the AIME. This is very, very important. So actually 60% of the calculation problem, they will get involved with the cosine law. So try to remember this. Okay. This is our number 9. This is now number 8. And then we go to our number 9. Our number 9 is actually centroid. So what is a centroid? Centroid means you have a triangle A, B, C. You have 3 mediums, right? AA prime, BB prime, CC prime, right? 3 mediums. The 3 medians will be intersecting at each other, right? At a point. We call it O. Okay. There is a very important property for the O, which is O, which is the centroid, is going to cut the medium into 1 to 2 parts. Is that right? So A prime O over AO is going to be 1 over 2. This is actually a very important property. AMC sometimes just test it directly. Okay, the centroid is going to cut into 1 to 2 portions. Only the centroid. Some other points, they won't be able to have the similar properties. In our regular lecture, we talk about so many centers, but only centroid has such a beautiful property, and it has nothing to do with the shape of the triangle. Any kind of triangle, they should have the centroid property all the same. Okay, this is number 9. Okay, let's go to number 10 property is how to determine the area of a triangle. How to determine the area of a triangle, because the area method is actually a very important thing for the AMC as well. So we like to give you guys some quick summary. There are how many ways to determine the area of a triangle? Okay, I think the first one is pretty much what you learned from elementary school. This is H, this is A, right? So the area can be written as 1 over 2 H times A. That's it, right? Nothing really special. Well, the second one is, this is actually something more important for the AMC. As long as you have a triangle, gives you 2 sides and also the included angle. So this triangle's area can be written as 1 over 2 A times B sine theta, right? The product of 2 sides and their included angle's sinusoid value is going to give you the area of this triangle. Same thing if this is beta, if this is gamma, it's going to be 1 over 2 BC sine beta, 1 over 2 AC sine gamma, right? This is the way how you organize your 2 sizes and also the included angle. The other one is the Heron's formula. I think we just talked about it previously. P equals to A plus B plus C divided by 2. S will be P, P minus A, P minus B, P minus C. Okay? And another thing, triangle ABC, I have what? This is R. R is what? R is the radius of the inscribed circle. R is the radius of the inscribed circle. So the area will be what? 1 over 2 R times S times P. Maybe I'll use a different word. P, where P is the parameter. P is the parameter of the triangle, right? 1 over 2 R times P. And the last one is when you have a circumcircle, A, B, C, the S can be written as ABC times 4R, where R is the radius of the circumcircle, right? R is the radius of the circumcircle. So generally speaking, these are the 5 most commonly used ways to determine the area of a triangle, and AMC will test you from time to time in different forms, all right? So try to remember them. It's actually very important for our calculation purpose. Okay, so this is actually our number 10. Let's go to our number 11. Number 11 is the famous many laws. Many laws go something like this. As long as, excuse me, as long as you have a triangle and you have a transversal line which cuts the triangle, right? Means A prime, B prime, C prime is a transversal line. It cuts the triangle into B prime, C prime to the two sides and extend your BC. It actually intersects with the extension of BC at A prime point. Okay, this is actually a very generic form. As long as you have this, you should have such a relationship, right? We have talked about it so many times in our regular lecture. So here, we just list it out fairly quick. This is your Menelaus, right? The Menelaus is actually an intrinsic property for all the triangles, right? You don't need to have any flowery things for the triangle. You will automatically have such a Menelaus relationship. Okay? This is the Menelaus. And the other one, as long as you talk about the Menelaus, you'll talk about the Siva. They are kind of a twin brother, right? They're the twin brother. So what is the Siva? Siva says something like this. You have a triangle and ABC. You find a dynamic point O inside a triangle. Make a connection, 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 A prime, B prime, C prime. Okay, then automatically you should have AC prime, BC prime, BA prime, CA prime, CB prime, AB prime equals to 1, right? So the Menelaus and the Siva, they're actually two very important theorems which reveals the proportional relationship within a triangle, any kind of triangle. It does not have to have any specific features. However, these two theorems will always hold for all the triangles. Okay? So this is our Menelaus and the Siva. Okay, try to remember. So for the Menelaus and Siva, I have to say, if you directly go to AMC10, they won't test you. I'll make it very straight. They won't test you. But as long as you're selected from the AMC10, you want to go to the AIME, this is a must-know knowledge for AIME. If you check all the AIME exams, as long as they test you for the AMC, for the Menelaus and Siva, it's pretty much roughly question number 4 to question number 7. This is for AIME, okay? It means that these are considered to be relatively basic problems for the AIME, right? Not super complicated problems for AIME. So that being said means you have to know this in order to go to AIME. But AMC 10 won't directly test you this, that is for sure. So I'll just give you guys some statistics, how these two exams are allocated, talking about different concepts, okay? Okay, a student asked me how many questions in AIME? There are 15 problems. 15 problems in AIME. All right, so that is pretty much number 12. Okay, so let's go to number 13. Number 13 is talking about, we're going to do a quick discussion talking about quadrilaterals and also the polygons. Okay, so we actually, in our regular lecture, we spend a lot of time talking about a triangle, but we didn't spend too much time talking about the quadrilaterals and the polygons. And the reason behind that is triangle is the basic unit for the entire 2D geometry. All those kind of polygon, like an octagon, polygon, all those kind of hexagon thing, everything, as long as you see polygons, your first reaction is try to break the polygon into different triangles. Okay, this is a number 1 rule for all the AMC exams. Normally speaking, you won't spend too much time for the polygons itself. Break them into different triangles, and taking from there, you'll be able to do your work. All right, even though you really have to use the polygons, most of the time, you will try to break them into some familiar shapes. Let's say square or rectangle. You won't be able just to deal with a regular polygon, and you really have no idea how to deal with that. All right. So that being said, I think that's the most important problems, like the strategies that you need to know in order to go to the AMC10 and AIME. So these are short and brief summary for all those concepts. Okay. And another very important thing before we really jump to the problem is actually when we talk about the congruency and similarity, right? So these two things are actually two important strategies that we keep using from time to time. At least you need to know what is the property for the congruency and similarity and how to determine the determination rule for the congruency and similarity. And the last one is how to find all the similar triangles and how to find all those congruent triangles. We already summarized a lot in our regular lecture. So in our bootcamp, we just give you guys big direction. There are so many ways to determine. And most of the time, this is a combination between the similarity and congruency together help you to solve the problem. All right. So before we jump to the problem for today's lecture, I'd like to give you guys a big overview, something fairly quick. For the entire 2D geometry, they basically test you three things. We're not talking about AMC, so the entire 2D geometry. They just basically test you three things. One is determine the angle. The question might ask you to determine what is the measurement for angle, or try to prove two angles that are the same, or one is like another, like twice of the other, or three times of the other, right? Second part is side. The question might ask you to determine the measurement of a side, or try to prove one segment is twice of the other segment, three times of the other segment, so on and so forth. The last one is the area or volume. Volume was more like for 3D, but it's kind of related for the 2D, right? So as long as you have a shape, the question might ask you to determine what is the area, and of the 3D thing, what is the volume. Okay. However, from the AMC's perspective, they barely test you the angle. Very minimum, very, very minimum. And the reason behind that is you can guess. Why? Because AMC is what? It's a multiple choice exam, right? So they must give you options A, B, C, D, E, right? If they ask you to determine the angle, there are only two things, two possible ways. One is they might give you some segment, and then you need to use the trigonometry to determine what is the sine value of this angle, and taking from there, you want to determine the measurement of the angle. But think about it, in our, what should I say, in our high school territory, we won't be able to determine too many flowery triangles, or like too many flowery angles trigonometry. We're basically doing something like 0, 15, 30, 45, 75, and 90. Something like this, right? Maybe also 16 in the middle, right? That's pretty much everything that you can determine simply using the trigonometry. So that being said, the AMC won't test you too much. Second is you can always have your protractor, right? If the question give you a problem, let you to determine the measurement of an angle, you can always try to make a perfect shape and pull up your protractor, do a measurement, and pick up the closest one from A, B, C, D, E. And that's it. So that being said, AMC won't test your angle too much because angle is so conspicuous. While AMC will focus more testing for the side and the area. If you go to your AMC exams, you check out, you're going to find pretty much 95% the problems, as long as they ask you, will be focused on the area and the side. All right, this is only a side note before we jump to the problems, because I don't want to spend too much time for the angles where you can directly pull out the protractor, measure it, and choose from A, B, C, D, E. All right, so after we talk about all those strategies, I want to give you guys some very typical problems that you might see for the AMC exam. And taking from there, we will see what is the common strategy that you can do in order for the AMC exam. So this is the second part, common problems. Okay? The first common problem is using similarity and its property. using the similarity and its properties is going to help us to do a lot of AMC exams. Let's have a quick look. See our first problem. Number 1. Okay. The first problem we have here is a problem from 2018 AMC10A, question number 23. Okay. They are considered to be the last 5 problems in AMC. So let's check it out. So the problem says what? So there's a farmer, Pythagoras, has a field in the shape of the right triangle. The right triangle's leg has 3 and 4. Still remember our Pythagorean triple, 3, 4, 5, right? This is actually a common number for the AMC. In the corner where those sides meet at a right angle, he leaves a small unplanted square S so that from the air, it looks like a right angle symbol. So he basically put a small part, which is pretty much empty. Okay? So the rest of the field is planted. The shortest distance from S to the hypotenuse is actually 2 units. The shortest distance, aka means what? You want to make a perpendicular line, right? Because between this, like between the point and a line, the shortest distance is actually perpendicular. Okay, so this is 2 units. This is a perpendicular line. With all those information together, the question asks you to determine what is the fraction of the field is planted. Fraction means pretty much you want to do a kind of do a division, right? You want to determine what is the area for this small square over the area of this entire triangle. Okay? A problem like this, how do you think? This is the most important thing, right? So as long as you see such a problem, it looks like your goal is trying to determine just basically one thing. What is this x, right? Because your square basically has a side length, which is x. You want to determine the x square over the entire triangle's area. Triangle's area is easy. This is 4, this is 3, this is 5. So this is going to be 6, talking about their area. So the $1 million question is try to figure out what is the value for x. Okay, we keep saying in our lecture, in order to determine a specific segment, this segment must have some interactions with our shape. If it is like flying there in the middle of nowhere, has no interactions, there's no way for us to solve the problem, right? So how to bring it into the entire picture, have the interaction is the most important thing, right? I think we should be on the same page. Okay, now X is actually squeezing there in the corner, but I want to make some interaction. My big interaction is actually my big triangle, right? But there's only one big triangle. There's only one tiny cube there. I don't think there's too much I can do. So therefore, auxiliary line is going to help you to solve the problem, right? How to add our auxiliary line? I think this problem is very conspicuous as well. I want to transfer this x into as many places as possible. So therefore, it might have some interaction with the entire shape. So what I will do is I'm going to make an extension from here and extension from here. Now I extend the 2 sides of the square, make sure it intersects with the entire shape ABC. At this moment, I think I can give some name. This is A. This is A. This is B. This is C, right? As long as I make an extension, this is going to be H. This is going to be G. This is going to be M, okay? M. And this perpendicular foot, I'm going to give a name maybe G, okay? So that being said, as long as I make this extension, let's check it out. If I want to do a quick thing here, I can basically put this x from here to here, right? This will be perpendicular. This should be perpendicular. This is quite understandable. You want to extend it to make sure it has more like a larger region to be reached, right? So I'm going to give a name maybe K here. I'm going to give a name maybe N here. Okay, this is not so important. Okay, think about it. At this moment, I might have a bunch of things. My X come to here. So let me see. That being said, okay, I will be able to have, this is a small triangle, right? In blue. This is a small triangle in red, right? This is a triangle in brown. And this is a triangle in green. Okay, there are so many triangles. So these triangles, all of them, they can get involved into my picture. I might do some of the work from these triangles. And obviously, these triangles are all similar to each other. Is that right? Are all similar to each other. So let's check it out. How are we going to use the similarities property and to solve the problem? Obviously, my triangle, let me change the color to EHG is similar to triangle CBA. Let's say this is E, okay? EHG is where? EHG is my triangle here. This triangle is basically similar to the entire big triangle for sure, right? And you're gonna have such a relationship. EH over 2. EH is actually what I'm trying to determine here, right? EH over 2 is actually equal to 5 over 4, right? EH is here. Let me change the color. EH is here, my blue one. 2 is this direction, right? 2 is the one of the right leg for this right triangle. This guy over this guy equals to, for the entire big triangle, is actually the hypotenuse over 4. 4 is here, right? Of course, I'll be able to determine the value for EH. EH is 5 over 2. Okay, this is 5 over 2. If this is 5 over 2, this is also 5 over 2, right? The outside is also 5 over 2. Okay, what else I can do? Check it out from here. My triangle BKH is also similar to HEM. Let me try to use the second one, BKH. BKH is my little triangle here. Let me use this color. Okay. Okay, this is good. It is here, right? BKH is my tiny triangle here. This one is actually similar to HEM. 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 My relatively bigger triangle here, right? So these two triangles, the brown triangles, are actually similar to each other as well. So that being said, I'm going to have what? KH equals to X, then BK equals to 3 over 4X, right? This is also get involved into the entire similarity. So that being said, let's check it out from here. BK plus KD plus DA. BK is here. KD is here. So this one I could give a name D. KD is here. And DA. This is X, right? BK is what? BK is actually 3 over 4X. We just calculated. And KD is what? KD is 5 over 2. But the entire one is actually equal to what? Entire one equals to 3. So you will be able to list out an equation, right? Based on the similarity segment we just calculate out. So what we're going to have? You're going to have 3 over 4X plus 5 over 2 plus X. These three guys. actually equals to 3. Is that right? You find out the relationship between the side panel, right? 3 segments, putting them together, you have 3. So therefore, x will be equals to 2/7. As long as you have 2/7, put it out here, right? This is going to be the ratio for these 2 parts. The ratio will be equals to 2/7 perfect square over this 6. The value is 2/147. 2/147. So that's going to be your D option, right? 145/147. Okay, so for such a problem, I think this is a fairly straightforward problem. Well, the most important thing is that as long as you see a similar triangle-like problem, try to extend all those segments all over the places and try to calculate as much as you could. And taking from there, you'll be able to list out some equations, right? From the equations, you'll be able to solve the problem. This is actually a very common strategy for the AMC problem. Try to list out some equations using the similarity, and taking from there, you'll be able to solve the problem. Okay, so far, so good? This is our first sample problem. Okay, if all good, let's go to our second sample problem. The second sample problem is a problem that we get coming from 2017 AMC10B, question number 21. This is exactly the same as the first problem that we mentioned, and you will see these are very common practice for the entire AMC. Let's check it out, okay? The second problem comes from here. You have a square with the side length x. You see, this is almost the same, a square with the side length, right? It's inscribed in a right triangle with the side 3, 4, 5. You see, the numbers are even the same. So AMC problem has a lot of patterns. They keep using the same problem, doing a lot of variations. So these numbers are pretty much the same. So that one vertex of the square coincides with the right angle vertex of the triangle. A square with the side y, this is another square, right? Is also inscribed in another right triangle, also with the side 3, 4, 5, so that one side of the square lies on the hypotenuse of the triangle. So basically, you're using the same right triangle, you inscribe 2 things, right? And then the question is asked you to determine what is the ratio between the 2 side lengths. So let's check it out. What is the question is asking for us? For all the geometry problems, it is always important that you have a perfect, if not super perfect, let's say in this way, graph. As long as you have a perfect graph, it's going to help you to do a lot of thinking, especially when the problem gives you a lot of tricky numbers. Like I said previously, you can automatically create a right triangle or find out the isosceles triangle or even a specific shape of triangle. If you have a perfect shape, it's going to help you to solve the problem significantly. So let me try to do the thing. Okay, these are the two shapes asked by the question. So you have, this is 3, 4, 5. You're inserting an x as a square. Same thing, 3, 4, 5. You're inserting a y as a square. Okay? And the questions ask you to determine what is the ratio between the x and y. Okay? Again, how do you think the problem? It is very important. As long as you see such a shape, something is inserted into another thing. Most likely, you're going to have a triangle, or you're going to have a square, you can have a rectangle inserting each other. A conditional react, as long as you see this insertion problem, there must be similarity. Okay? I'll tell this for sure. As long as you see any insertion problems, then for sure there will be similarity get involved. No exception, always go for this. Okay, if that's the case, who can tell me what is the similarity I need to do in order to determine what is the x, what is y? Like I told you, as long as you see insertion, see, these two problems exactly the same. This is also insertion, right? And here you have two insertions, here, here. As long as you see the insertion, then for sure there will be similarities. Now, who can tell me what are the similarities in such a problem? You can always put your thought into the group chat, as I'm always monitoring the group chat for our entire lecture. Okay, where you can find these similar triangles. Okay, I see somebody has the correct answer. Okay, Rich is perfect. Yeah, it's exactly the same thing. You see, my first similar triangle actually sits here. My first similar, see, this is one line, another line, three lines, they create a similar triangle, right? This triangle will be similar to the big triangle. Is that right? This triangle is going to be similar to the big triangle. Let's say I give a name, A, B, C, D, E. Then for sure, triangle ADE is similar to triangle ACB, right? And you're going to have what? AD over X is equal to 3 over 4. So therefore, AD is what? 3 over 4x. This is 3 over 4x. Is it right? As long as you have the 3 over 4x, like I said, always try to use the similarity to calculate the measurement of the segment and then try to construct an equation, right? So check out from here. Check out from here. You're going to have 3 over 4x plus x equals to 3, right? Because the question already gave you the measurement for the short leg. It's 3. So therefore, x is 12 over 7. This is exactly the same thing as we did for the previous problem. Try to find out the measurement for the segment. Try to find out the measurement for the segment, and then try to construct an equation. This is always the case for most of the AMC problems. Okay? This is exactly the same thing I did for here. Construct the equation, figure out the value. Okay? Since I give you already some information here, who can tell me here, how can I do exactly the same thing? How can I do exactly the same thing for such a shape? Try to learn what I got from here. You always try to use the similarity to determine some segments, right? As long as you have the segments in hand, you will use it to construct an equation. These are the very important 2 steps for pretty much all the problems. Yeah, I see somebody already has the correct direction. Yeah, pretty much doing the same thing. You want to do some calculation. This time, maybe do some magic from here. This part is already y, right? Because this is a square. If I can do some magic to figure out a value for this guy and figure out a value for this guy, again, I'm going to put everything together as an equation, right? And then I get what I need. So the thinking process are exactly the same. You don't have to do too many problems, 1 or 2. You get an idea, we're good to go. Okay, so how to do that? Let me change the color. A, B, C, D, E, F, G. I have to put all the names. So triangle ACB is actually similar to triangle AGD, right? Obviously, this triangle is similar to the big triangle. So therefore, you have AB over Y will be equal to 3 over 4, right? So therefore, AB will be 3 over 4y. This part is going to be 3 over 4y. If you did it once, you'll be able to do it for the second time, right? Exactly the same thing. You don't have to think too much and you get what you need. Okay, so this guy, triangle EFG, is also similar to triangle ADG, right? So if this guy is y, you'll be able to figure out this is 4 over 3y. Same thing. I don't have to spend too much time doing the same thing, right? So it's pretty much the same thing. One corner there, one corner there. You'll be able to determine the length for FG. So FG will be equals to 4 over 3y. As long as you have this, the last step is doing what? Find out a place you can have an equation, right? This is the place you can do an equation, right? So that's going to be what? 3 over 4y plus y plus 4 over 3y equals to 5. Exactly the same strategy as we did for the last problem. So y will be 60 over 37. The number is a little bit nasty, 60 over 37, right? And the question is asked you for determine what is the value for x over y. That one is easy. You just plug in the value, 37 over 35. 37 over 35. Okay, so with these two problems, we have already come up with a strategy. The strategy basically has 2 steps. Step 1, using the similarity to determine segments, right? Try to figure out all the segments here, there, whatever, as much as you could. Step 2 is using all those segments you just calculated, you just obtained to have an equation. Is that right? Have the segment and then construct an equation, and you'll be able to solve all the problems. Okay? You'll be able to solve all the problems. And also, like I mentioned previously, trust me, as long as you see this insertion thing, probably you're going to see this similarity related properties. This is a big direction. As long as you see an insertion, one to another or two to another altogether, you're probably going to use the similarity to do the problem. Okay, so far, so good? If all good, let's go for another AIME problem. Okay, let's try to see how we're going to do this problem when you have something more difficult, an AIME problem. What are we going to do? This is the AIME problem. It's a problem from 2015, AIME 1, question number 7. Okay, let's have a look how you're going to do such a problem. So the problem says what? You have a diagram below. ABCD is a square. Okay, this is a square, and E is the midpoint of AD. Okay, E is the midpoint. Okay, I'm just gonna highlight it here. So this part equals to this part. Okay, it's the midpoint. And then point FG lies on CE, HJ lies on AB and BC, blah, blah, blah. So that FG HJ is also a square. FG HJ, rich guy? FG HJ. Okay, so this is also a square. Okay, point K and L lies on GH, MN lies on AD and AB, blah, 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 so that KLMN is a square as well. KLMN. Okay, this is also a square. Oh, it looks like they find some points, right? Very smartly find some points, put them together, and then they create two squares inserted into half of the big square, right? The big one is a square, and then you somehow find something, make it two insertions there. Okay, with all the information, the question gives you another very important condition. The area of KLMN is 99. Okay, this is the KLMN, right? Okay, the area of this red shade is 99. And then what the question asks you to determine what is the area of the, let me change the color. Okay, the area of the FGHJ, this guy. What is the area of this guy? The question gives you an area of the small square, ask you to determine the area of the big square. Okay, a problem like this, how are we going to do? How are we going to solve a problem like this? The thinking process is always very important. So this is what I see. Okay, I'm sharing. How do I think for such a problem? If you give me the area of this triangle, of this square KLMN, and then you want me to determine the area of the big one. So obviously, your KLMN and your FGHJ, these are two squares, right? They should be similar to each other, right? All the squares, they're similar to each other. All the equilateral triangles, all the circles, they're similar to each other, right? This is quite understandable. Okay, if the question asks you to determine what is the area ratio of two similar shapes, your first reaction should always be, anyone else? If two shapes that are similar to each other and the question asks you to determine the area ratio, your first reaction is always area ratio will be the similarities ratio's perfect square, right? This is like a golden rule you need to remember. Yeah, the area ratio is always the similarities ratio's perfect square. Similarity ratio can be considered as a side or the corresponding segment, so on and so forth. So this is like the golden rule. So it looks like my $1 million question is trying to figure out what is the similarity ratio between these two squares, or we can say the side ratio between these two squares. Okay, now we're on the same page. So the second step, this is step number 1, right? Step number 2 is let's try to figure out what is the side ratio between MN, HG, so on and so forth. Okay. If you can remember what I mentioned previously in my previous lecture, in my previous problem, I say what? As long as you see insertion, there might be some similarities, right? Do you still remember? All our knowledge are connected. Insertion must have the similarity. And this problem is exactly insertion. Is that right? You're inserting two squares into a big square. There must be a bunch of similar triangles or similar shapes. Let's check it out from here. we do not even have to do a very rigorous proof. You can find out. I think all the right triangles in this shape, they're similar to each other. Is that right? I'll take one. This is one portion. This is two portion, right? Everyone is going to be one portion, two portion, all over the places. Is that right? Okay, I'm going to erase this. Okay, all the right triangles, they're similar to each other. And your problem is asking me to determine what is the side ratio between these two squares. This is the tricky part for this problem. Let's check out these two shapes. One is AMLH. AMLH. Let's check it out, okay? The other one is the BHGC. Let me change a different color. BHGC. BHGC. Okay. Now I'm talking about two quadrilaterals, right? Two quadrilaterals. So these two quadrilaterals, can I say they're also similar to each other? Can I say these two quadrilaterals are similar to each other? That is my question. AMLH, BHGC. These are two quadrilaterals. They're not like a triangle, square or something. They're just like a random, right? Two quadrilaterals. Well, how can I say these two quadrilaterals are similar to each other? Let's check it out. These two quadrilaterals, they both have two right angles here, right? And what about this angle? And this angle? Like I mentioned previously, because you have the insertion, so I said there must be similarities. And then I have quickly provide all those right triangles that are similar to each other, right? Everyone is this is one portion, this is two portion, right? This is also one portion, this is two portion. Everyone is 1-to-2 relationship. So that being said, all those right triangles, they're actually similar to each other, right? So that being said, my blue dot is going to be the same as my blue dot. Is that right? As long as my two blue dots are the same, so my last angle, this guy, will be also equal to this guy, right? Because the total sum of all the angles within the quadrilateral is 360. You already have one right triangle, another right, like one right angle, another right angle, and the blue dots are the same. So the remaining, the last one is also the same. So far, so good? So that being said means what? Means these two shapes are actually similar to each other. Is that right? These two shapes are similar to each other. Why I'm doing this? I'm doing this for a reason, because you wanted me to determine what is the similarity ratio between the square ML. Let's say this is ML is actually one side length, right? The other one is what? HG. You wanted me to make the difference, like the ratio between the two. And I need to find some shape where to handle it. Luckily, I find out one is here, color, change the color here. One is here as one side of this quadrilateral. One is here as one side of the quadrilateral. Okay, so that being said, if for some reason I can figure out a similarity between these two quadrilaterals, then I will be able to figure out the ratio between these two squares, and then taking from there, I get what I need. So far, so good? So this is the way, right? This is the thinking process, right? I need to put these two places into two shapes. So these two quadrilaterals are the perfect place for me to put. As long as you know this problem is almost done. Let's check it out. I'm going to make a one auxiliary line here, but this is not a super complicated thing. I'm going to make a hypotenuse, like the height for the hypotenuse. Again, this little triangle will also have the 1 to 2 relationship, right? Because everyone is similar to each other. If I say this is A, this part is A, so this part is going to be 2A, right? Okay. If this part is 2A, this part is going to be 4A. Is that right? This is quite understandable, right? Everyone is 1 to 2 relationship, right? Okay. My goal is doing what? Exactly. Say I want to calculate all the measurement for all the segment, and then somehow I can figure out an equation, right? I just want to have an equation, and then we're good to go. Okay. If this is A, let's check out from here. Let me change a different color, maybe to green. This triangle, this green-shaped triangle, and this green-shaped triangle, they are actually what? Congruent to each other, right? They're not only similar, for sure, everyone is similar, but this is even better than similar. They are congruent to each other. Is that right? If they are congruent to each other, okay, this is going to be 2A as well, right? This is going to be 4A as well. Is that right? So far, so good? Okay, now I'm almost there to have an equation. My equation is what? This part, let's say AH plus HB is actually equals to the side length of the big square, which is BC here, right? AH plus HB. HB is here. I just calculated 4A equals to BC. BC is everything there, 7A. So therefore AH is what? 3A. This is my equation, right? 3A. 3A. Okay. You know what? We're done. Why? Let's check it out. Change the color. Where's my AH? AH is here. AH is one side of this AMLH quadrilateral, right? And what is the corresponding side for AH? What is the corresponding side for AH? It should be BC, right? BC, right? In the bottom one. So that being said, AH over BC, AH over BC reaches 3 over 7. This is the similarity between these two quadrilaterals, right? If they are the similar, this is similarity. If this is the similarity, it also means ML, HG is also the similarity, right? So that being said, ML over HG is 3 over 7. Yeah, this is AIME problem. It's a little bit tricky compared with AMC, but the strategies are exactly the same. You want to use the similarity to create a what? An equation. From the equation, you will be able to determine the segment. And from the segment, you luckily find out these two black segments, their ratio is also the similarity for these two weird quadrilaterals, right? And so what you are trying to determine, ML over HG, is exactly the same similarity. So therefore, you can find out the area between this small square, a KLMN, area between the big square, FGHN, is going to be exactly 9 over 49. Is that right? As long as you have that, the question already give you the area for the small one. You can determine the big one right away. So the big one, FG, HJ, is exactly 539. That's it. So the thinking process is exactly the same. As long as you see the insertion, there are similarities. As long as you have similarity, try to use the similarity to determine the segments. And as long as you have all the segments there, try to use the segment to have an equation, and then you get what you need. So these thinking process are exactly the same for all the problems. So far, so good? Okay. So this is actually the first type I want you guys to remember. Using the similarity have such a pretty much a routine. Okay? If all good, let's go to the second type that you need to know. It's actually using the Pythagorean Theorem. Pythagorean Theorem is actually so familiar to everyone, right? So I like to just give you one problem. One problem to help you guys to kind of like a quick reminder how to use the Pythagorean Theorem, and we're good to go. This is a problem from 2004, AIME 2, question number 12. Even though it's a number 12 problem, if you use the Pythagorean Theorem, it's like so easy. Trust me, this is not as crazy as it looks like, but it's like so easy as long as you know what to do. Okay? It's one here. Okay, this is the AIME problem. So this AIME problem says you have an isosceles trapezoid. Okay, and then give you a bunch of numbers or the side lines, blah, blah, blah. You want to draw a circle of radius 3, centered as A and B, circle of radius 2, centered as C and D, and then make sure they are as close as possible. And then you want to make a small circle in the middle to make it tangent to all the circles you have already drawn. And the question is asked you to determine the radius of this circle. This is like a typical AMC way to ask you. Instead of ask you directly the radius of the circle, they always want to give you a weird thing. So this circle, let's say the radius can be written as m over n, and then the question asks you what's the value for m plus n. This is a typical AMC way to ask you. You know what? And the reason behind this, they don't want you to guess. If they directly ask you what is the radius for the circle, you do a perfect shape and then you use a ruler to measurement. Like to do a measurement, then AMC won't be able to know that, right? So they give you something like this, give you something like this, and then you want to add M, N, P, Q all together. There's no way for you to guess, right? So that's part of the tricky part for AMC. But nevertheless, the question is ask you to determine the radius. So let's check it out. How are we going to do such a problem? Also, like I mentioned previously, all those kind of AMC problems, you need to have a good graph. As long as you have a good graph, you're good to go. So this problem says you have such a shape. This is a isosceles trapezoid, and you want to make a bunch of circles. These are two circles. These are three circles. With all those information, you want to make a little tiny circle in the middle. And the question is asking you to determine what is the radius for the tiny circle in the middle. Okay? Yeah, this is even though question number 12, but I think this is a relatively easy problem. Okay? How to do such a problem? This is also a very typical problem for pretty much all the AMC. And there's pretty much a follow the pattern how to do such a problem. You don't even have to think. You just follow the pattern, you know what to do. So step number 1, as long as you see a trapezoid, what kind of trapezoid? They give you the value for all the size A, B, C, D, right? This is pretty much the same. your step number one, always step number one is to determine the height. Try to determine the height. Even though you might not use it, you might use it, I don't know. But as long as you see a trapezoid, it gives you a bunch of like all the sizes. Step number one is try to determine the height. Okay. In our case, this is even easier. This is B. This is also B, right? It's the same thing. So you will be able to determine the height right away. So let me change the color. Using Pythagorean are good to go, right? So this is 2, this is 2, this is 1, and this is 5. So the height will be under root 24, right? Under root 24. The height is under root 24. Okay? As long as you see the height, you're going to go to step number 2. Step number 2, as long as you see circle tangent to each other, you're probably going to do all the magic from this tangent point. Do you still remember when we're talking about the tangent? We're talking about as long as you see tangent, always do a connection between the center to the tangent point. Always do a connection between these two centers, always using the tangent secant theorem. This problem, I don't think you want to use the tangent secant theorem, right? Because there's no point outside. But still, you want to do the connection between the centers. You want to see the tangent point, like the connection from the centers to the tangent point, right? I think that's quite common sense. Most of our magic is going to happen around this tangent center, the two centers, and also the tangent point. Let's check it out. So if we do a quick summary for this part, this is exactly, you see, these are the connection between the circles, and also they have the tangent point, right? This is exactly what we mentioned in our previous section. So what are you going to have here? So this part, this is going to be 2, right? This is going to be your R. So you will be able to determine this part, right? Let me give a name. This is maybe E. This is F. This is O, right? So you're going to have EO will be this equal to what? R plus 2 square minus 2 square, right? This is EO. The other one, FO. FO is exactly the same thing, right? Our strategies never change. Here, this is going to be 3. This is my R, right? So OF equals to what? OF equals to 3 plus R perfect square minus 3 perfect square, right? This is 3. Is that right? Okay. Do you still remember? All those kind of problems have the same strategy. You do either the similarity or like whatever, you figure out all those segments, and then taking from there, you want to do an equation. Always doing an equation, right? The equation will be what? EF plus OF equals to your height. Your height is under root 24, right? EF is here with your R. EO is here with your R, and OF is here with your R. Is that right? This is exactly the same strategy as we mentioned from day one. Nothing has been changed. You're going to have under root 2 plus R square minus 2 square, under root 3 plus R square minus 3 square equals to under root 24. You have to figure out this equation by yourself, right? So, but nevertheless, you'll be able to figure out R equals to a pretty nasty number, minus 60 plus 48 under root 3 divided by 23. And this is going to be your MNKP. So the total answer, KP will be 134. Will be 134. Is it good? This is actually the thinking process I like to guys to remember. Okay? This is actually the thinking process. How do you see a problem? So all those problems are actually quite similar. Our strategies never changes, right? As long as you see a trapezoid, try to determine the height. As long as you have your segment, try to create an equation. With all the information together, you will be able to solve the problem fairly quick. Okay, so try to remember our strategies are very consistent across the entire board. Okay, this is the second important thing, the typical type of problem using the Pythagorean rule. So because you're so familiar with Pythagorean rule, so I don't have to give too much question, all right? So let's continue. Our third category in the AMC exam from time to time is try to remember some trigonometry values. Try to remember some trigonometry values. This is going to help you to accelerate your calculation process. Where I come from? Let's have an example to demonstrate what I'm trying to say. This is a problem we're looking at from 2015 AMC10B, question number 22. Okay, let's check it out. So this problem says, in the figure shown below, ABCDE is a regular pentagon. Regular pentagon. And AG is equal to 1. Okay, so AG is equal to 1. AG is just here. I'm just going to highlight it. AG is here. That one equals to 1. Okay, with all those information, the question asks you to determine what is FG plus JH plus DC. Okay, first thing first, like I told you previously, as long as you see all those pentagon, all the weird gons, so on and so forth, so there you don't even have to think about too much. You can basically focus on the triangles, right? Break the entire part into the small triangles and do your magic from the triangles, right? So don't be scared whenever you have a, like a pentagon or polygon, so on and so forth. Okay? And moving forward, how can I solve such a problem? How can I solve such a problem? So according to the official solution from the AMC, this is the way how they solve the problem. We can check it out, like the official solution first. Okay? So the official solution says a quick observation I can find out. Check it out from here. JH is actually the same as EF, right? Because this is actually a what? This is actually a parallelogram, right? According to like the regular pentagon, this is going to be a parallelogram. Okay? And also, my DC is the same as EG, right? DC is the same as EG. Again, this is also a parallelogram. This is also, the big one is also a parallelogram, right? I think this is understandable, right? Because you have a regular pentagon, you'll be able to do such some kind of moving. So that being said means what? EF is equal to JH and EG is equal to DC. So that being said, all my 1, 2, 3 segments will be kind of squeezed into this little one here, right? As long as I figure out this, my work is done. So I'm going to drag it out. I'm going to drag out this little segment here. This is my A, E, G. This is my F. Okay? According to this AMC's official solution, it says something like this. Because you have the pentagon, right, it's a regular pentagon, then you will be able to determine this guy is actually 36 degrees. This is not a magic, right? This is also 36 degrees. This is also 36 degrees. So I'm going to put it here, 36, 36, 36. And this guy will be what? The exterior angle will be the sum of the two not adjacent interior angle. This is going to be 72. And this is going to be 72 as well, right? So it says triangle EHF is actually similar to triangle AFG, right? So the big triangle EAF is actually similar to this small triangle AFG, because they both have like 36 at the top and 72 on the bottom. As long as you have this, let's say I want to say this is X, just for instance. Okay, this is going to be 1, right? Why? Because the question says this is 1. This is 1. If this is 1, this is also 1, right? If this is 1, this is also 1, right? You'll be able to transfer all those segments inside our shape, which is understandable. Okay, so with that information, you'll be able to have 1 plus x over 1 will be equals to 1 over x, right? You're trying to figure out a similarity relationship between the big triangle and also the small triangle. So with that, x will be equals to y minus 1 plus under root 5 divided by 2. As long as you have x is here, x is here, right? Same thing. Then you will be able to know, okay, GF equals to x and GH equals to 1 and DC equals to 1 plus x. Is it right? Right? Let me read. X is here. GH is here. GH is actually equal to 1. And what about CD? CD is here. CD is actually 1 plus x. You already know the value for x. You'll be able to determine that. So the total sum for FG plus GH plus DC equals to 1 over 5, 1 plus or under root 5 divided by 2. Okay, so this is actually the official solution to this problem. So that's going to be D. Okay, this is the official solution to this problem. However, trust me, if you know something like, okay, so first of all, this is official solution. Okay, some students have some question. Oh, good. Okay, perfect. But trust me, you're wasting too much time doing this calculation. If you know some specific values, trigonometry value, specific angles, trigonometry value, you can actually solve this problem fairly quick without have to spend too much time doing the similarity thing here and there. So my solution number 2 is basically taken from here. If you want to determine the value for FG, okay, I'm just gonna do a quick a quick perpendicular line here. Okay, so as long as I can determine the value for, let's say, GP, my FG is going to be twice of GP. Is that right? My FG is going to be twice of GP. GP is here. Okay? Then what is the value for GP? GP is actually what? 1 times cosine 72 degrees. Is that right? This is 72. Let me zoom in here. This is 72 degrees here. My GP is here. My GP is here. So this is 1, right? This is actually given by the question AG equals to 1. So GP is directly equals to 1 times cosine 72 degrees. If you know the value for cosine 72 degrees, your work is done. So what is the value for 72 degrees? It's under root 5 minus 1 divided by 4. That's it. Just one step, you figure out the problem. Okay, you know what I mean? So FG, you can directly write as twice of GP, which is 2 times under root 5 minus 1 divided by 4. That's it. You get FG. As long as you get FG, you'll be able to determine DC, GH, FG. And you solve the problem in about, I don't know, 30 seconds instead of doing all those weird things. So that being said, sometimes if you know some value of some specific triangles, like specific angles, you will be able to expedite your calculation significantly. So that actually brings up to the very important side note here. Trigonometry value for certain angles. Okay? In our regular lecture, I think we have 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, right? But there are some extra angles. If you can remember, you can actually do the calculation fairly quick. There are 15 degrees and 75 degrees. This is one pack. The other pack is 36 degrees and 72 degrees. If you can remember the value, accurate value for those guys, it's going to help you to do your calculation significantly. So I like to give you the value for you guys to remember. Sine 15 degrees is actually equal to cosine 75 degrees, equals to under root 6 minus under root 2 divided by 4. Sine 75 degrees is equal to cosine 15 degrees. It's under root 6 plus under root 2 divided by 4. Okay? The other pack is cosine 36 degrees is equal to sine 54 degrees equals to under root 5 plus 1 divided by 4. Cosine 72 degrees is equal to sine 18 degrees under root 5 minus 1 divided by 4. Okay, try to remember those specific numbers and you'll be able to do your calculation very fast. So how to do this? I'm just going to give you a quick direction because this is not a trigonometry section. We don't have to say too much. Let's say sine 15 degrees will be equal to sine 45 degrees minus 30 degrees, right? So you will be able to use the two angles sum and difference trigonometry to determine the value for this. Is that right? So this is going to be sine 45 cosine 30 minus cosine 45 sine 30, right? The other thing is exactly the same thing. You'll be able to determine the specific value for specific degrees. As long as you know this, all those problems in the future, don't waste your time doing this similarity determination, calculation, so on and so forth. Totally waste of time. Directly using your cosine 72 degrees, and you solve the problem in about 30 seconds. Okay? So far, so good? This is the very important thing I want you guys to know. This part, solution number 2. Directly using the cosine value for specific angles, and you will be able to accelerate your entire calculation process. Okay? If all good, let me give you another sample problem. That is a problem from 2014, 2014 AMC10B, 10A, question number 22. So this is another AMC problem. It says you have a rectangle ABCD, and AB is equal to 20, BC is equal to 10. Let B be the point on the CD segment such that CBE angle equals to 15 degrees. So the question asks you to determine the value for AE. Let's check it out. You have a rectangle. You have kind of a shape here and a shape here, right? The question says you're going to have A, B, C, D. Okay, this is 10, this is 20, and this is what? 15 degrees. This is 15 degrees. Okay? With all of the information, the question asks you what is the value for AE? What is the value for AE? Okay? So if you check the official solution from AMC actually take a huge round. So they do a lot of auxiliary line, try to do the calculation, blah, 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 and takes forever. And you still don't know, and you still do not know what they're trying to do. But if you remember the trigonometry value for 15 degrees, you will be able to solve this problem in about 30 seconds. What are you going to do? So in order to determine AE, right? As long as I know the DE, I use a Pythagorean theorem, it's good to go, right? How to know DE? As long as I know EC, I use 20 minus EC, I'm good to go. So therefore, I can do EC, it's actually equal to 10 times tangent 15 degrees. This is 10, right? 10 times tangent 15 degrees, which is 20 minus 10 under root 3. Tangent 15 degrees, you just use sine and cosine, do a division. We're good to go, right? I'm going to show you tangent 15 degrees equals to sine 15, cosine 15. It's going to give you 2 minus under root 3, right? You can just basically do the calculation on the fly. So this one is going to give you 10 times tangent 15 degrees. As long as you have EC, so moving forward, DE will be what? DE will be DC minus EC, which will be 10 under root 3. And then using a Pythagorean theorem, AE will be equal to 20 degrees. Like 20. AE will be equal to 20. That's it. Don't waste your time. Like the AMC official solution, it really drives you nowhere and totally doesn't make sense. Okay? So this is actually the way how you're going to determine the value for AE. That's it. So a quick recap for this. The most important thing for this section is ask you to remember as many specific angles, trigonometry value as possible. we already know 15, 35, like 50. I mean, we already know like 30, 45, 60, so on and so forth. And on top of that, try to remember this 15, 75. And this, let me try to erase here. And also 36, 72. This is going to be very helpful for our entire determination process. Okay? So in today's lecture, we actually introduced the 3 very important concepts for the 2D geometry. Let's do a very quick recap. The first one is using the similarity. As long as you see some insertion, all those kind of things, you should have the similarity. The big direction for the similarity is always try to use the similarity to calculate as many segments as possible. Some of them, you might even use them, but try to calculate, right? It doesn't hurt. As long as you have the segment, always try to do an equation. Try to always do an equation. And solve the equation, you will be able to get what you need. This is the first big direction. The second big direction is the Pythagorean Theorem. Pythagorean Theorem is very important. We learned that from like pretty much day 1. And there are some patterns how to use the Pythagorean Theorem. We introduced it here, if you can recall. As long as you see this trapezoid, pretty much most of the time you're going to use this Pythagorean Theorem. As long as you see a bunch of circles that are touching each other, we introduced strategies. Do connection between the centers. Do connection between the like tangent point and the center, and you will have a bunch of right triangles. Taking from there, you will be able to solve the problem. This is the second Pythagorean theorem. And the last one is try to remember some kind of like more value, trigonometry value for a specific angle. Because if you know this angle, you can actually save a lot of time talking about the calculation. You can just directly use the angle value and try to basically give the value right away. But it's up to you, right? Because AMC always have a solution, try to do all the calculation one by one and figure out. But if you want to remember some specific values, this is going to help you to expedite your calculation process. So this is like the 3 strategies I want to introduce today. In the next lecture, is this going to be, we still have something to wrap up for the 2D geometry, and I'm still going to give you some other patterns. And also we're going to talk about something about the 3D geometry. To be honest, 3D geometry is actually tested even more for AMC10 rather than AMC12. Okay, AMC12 didn't test the 3D geometry too much because they have too much other concepts they want to test. But AMC10 actually put a lot of emphasis for the 3D geometry, which we will talk about for our next lecture. All right, I think that's pretty much for our today's lecture. You have any questions for me? I see there are some discussion in the group chat, but I think one student already answered the other, so that's good enough. Yes. Yeah, if you have no more questions for me, I hope you guys enjoy the rest of the weekend, and I'll see you guys for the next lecture. Bye, guys.